On paper, projecting 2,200 Marines into a high-threat littoral zone should be suicide. The physics hasn't changed since 1982. Any large metal object reflects electromagnetic waves like a mirror. One flat surface perpendicular to a search radar, and your detection range explodes. The Falklands proved it. British ships died because their radar cross-section turned them into floating billboards. Today, the USS Tripoli, LHA-7, and the 31st Marine Expeditionary Unit are doing exactly that in the Middle East. So how did engineers break a constraint that looked unbreakable for half a century? Map of Strait of Hormuz with shipping lanes highlighted. Slow zoom on USS Tripoli silhouette steaming west from Japan. Cut to 31st MEU loading stats overlay. The driver is simple, anti-access/area denial. Iran's coastal missile batteries and integrated air defense network turned traditional amphibious assaults into shooting galleries. The Tripoli isn't a full supercarrier. At 844 feet and 44,000 tons, she's a lightning carrier, optimized to embark the entire aviation element of a Marine Expeditionary Unit plus roughly 1,687 Marines, with surge capacity pushing past 2,200. She carries F-35BS, MV, 22 Ospreys, and CH-53K King Stallions. The entire force can be lifted ashore in hours, not days. But none of that works if the enemy sees you coming from 200 nautical miles away. Conventional fighter jet versus radar wave. Waves bounce straight back. Then F-35B appears. Waves scatter at crazy angles. Equation appears. Radar range equation R_max is proportional to RCS caret 1/4. Here's the first principle's truth. Radar works by the same Maxwell's equations that govern every electromagnetic wave. The power returned to the receiver is proportional to the target's radar cross-section, effectively how big it looks to the radar. For a flat plate at normal incidence, RCS scales with the square of the physical area divided by wavelength squared. A legacy fighter like an F-16 presents roughly 5 to 10 square meters, detectable at 150-plus nautical miles by a modern S-band radar. To hide an aircraft that weighs 30,000 pounds and carries weapons, engineers had to drive that number down by 3 orders of magnitude. Because the radar range equation has a cruel fourth-root relationship, cut RCS by 1,000 and detection range drops by roughly 5.6 times. Suddenly, the enemy's early warning window collapses from hours to minutes. That's why stealth isn't marketing. It's the only way physics lets you get inside the threat ring before the missiles fly. Exploded CAD view of F-35B, internal weapons bays, edge serrations, ram panels glowing. Side-by-side comparison, F-117 faceting versus F-35B curved but still faceted surfaces. CFD-style EM simulation, showing waves being deflected 90 degrees away from the emitter. Engineers attack the problem at the molecular and geometric level simultaneously. First, shaping. Every external surface is angled so that incident radar energy is reflected away from the emitter, not back. No right angles anywhere the radar might see. The intakes are S-curved. The canopy has a conductive mesh. The edges are serrated like a saw blade to turn specular reflection into diffuse scatter. Second, materials. Radar-absorbent material RAM, iron-carbon composites and dielectric layers, converts incoming electromagnetic energy into tiny amounts of heat instead of reflection. These coatings are tuned to specific threat bands used by Iranian systems. Third, internal carriage. Missiles and bombs stay inside the fuselage until release, eliminating the massive RCS spike of external pylons. The result? Official estimates and open-source modeling put the F-35BS frontal RCS at roughly 0.001 square meters, smaller than a golf ball. To an X-band fire control radar, it looks like a Sparrow, not a strike fighter. And because the Tripoli's flight deck is specifically engineered for style operations, larger elevator capacity, heat-resistant deck plating, and JP-5 fuel system scale for F-35BS unique thirst, she can launch and recover these aircraft in numbers that matter, up to 20 F-35BS plus Ospreys simultaneously. That's the hero moment. The ship and the jet were designed together, so the physics of stealth survives the realities of shipboard life. F-35B versus F-35 35C range/payload. Maintenance cost overlay. Marine and hangar pulling ram panel, showing wear. Cost comparison. $94 million per F-35B versus $13 billion for class carrier. But stealth isn't free. The ram coatings degrade in salt spray and jet exhaust. They require constant reapplication, a logistical nightmare at sea. The faceted shaping and internal bays add weight and complexity. The F-35B carries less fuel and ordnance than its carrier landing cousin. Specific fuel consumption rises because the lift fan system, brilliant engineering in itself, still burns extra kerosene for vertical ops. The ship itself had to accept compromises. No traditional well deck on the first two America-class hulls means pure aviation assault. Surface connectors come from the accompanying LPDs. Every extra ton of stealth material is a ton less of something else. And cost? Each F-35B runs nearly $100 million. The Tripoli herself cost over $3.5 billion. That's cheap compared to a Ford-class supercarrier, but it's still national-level money. Marketing claims of invincible are nonsense. Low observable is not no observable. Modern low-frequency radars and network sensors can still cue missiles. The stealth just buys the Marines the minutes they need. Tripoli at sea launching F-35B at dusk. Graph. Cost per deployed Marine for ARG versus traditional carrier strike group. Final shot. 31st MU Marines fast roping from Osprey. So is this technology actually viable for the future? Yes, because it already works. The Tripoli and her F-35BS have proven the concept in multiple deployments. The 31st MU's 2,200 Marines now have an air umbrella that can penetrate defended airspace long enough for Ospreys to insert recon teams, secure beachheads, and establish forward arming points. Economically, it scales better than full carrier groups. One Lightning carrier plus escorts can deliver Marine air-ground task force firepower at a fraction of the price and with distributed risk. That's why the Navy is building more America-class hulls. But physics still has a final vote. No coating lasts forever, no shape defeats every frequency, and no ship is unsinkable. Stealth simply moves the detection line closer to the enemy, giving human decision-makers the margin they need. Slow pull back from Tripoli's wake at sunset. Fade to equation. RCS reduced time gain mission success. Text. We didn't break the laws of physics. We learned to dance with them. Human. Economically, it scales better than full carrier groups. One Lightning carrier plus escorts can deliver Marine air-ground task force firepower at a fraction of the price and with distributed risk. That's why the Navy is building more America-class hulls. But physics still has a final vote. No coating lasts forever, no shape defeats every frequency, and no ship is unsinkable. Stealth simply moves the detection line closer to the enemy, giving human decision-makers the margin they need. Slow pull back from Tripoli's wake at sunset. Fade to equation. RCS reduced time gain mission success. Text. We didn't break the laws of physics. We learned to dance with them. Human ingenuity didn't repeal Maxwell's equations. We just spent decades and billions learning to make the waves go somewhere else. The 2,200 Marines heading toward the Middle East aren't riding magic. They're riding the most sophisticated compromise between physics and politics ever floated. And that, not hype, is what